Friends, today we will study excitation systems. In this topic, we will cover what are the excitation system requirements, then what are the basic elements of excitation systems, then the dynamic performance measures. The dynamic performance measures are categorized into two categories: large scale performance measures and small signal performance measures. Then we will discuss about the various control and protective functions which are provided in excitation systems. Some of the control and protective functions which we will discuss are AC and DC regulators, load compensation, under excitation limiter, over excitation limiter and field shorting. Now, we will briefly address to all these points. So far the excitation system is concerned, it plays very significant role in the stability analysis of a power system, and it is also very powerful control which can be used to improve the stability of the system. Here I would like to tell that over the years the different types of excitation systems for the synchronous generator have been developed. You know that we have in today our power plants the DC excitation systems, AC excitation systems, and static excitation systems, and in AC you have brushless excitation systems and the static or stationary rectifier excitation system, right. A variety of excitation systems have been developed, and this development have been possible with the development of the power electronics devices. Okay. We will go into these details as we proceed across or proceed with. Now, first let us see the basic function of excitation system. It is known to all of you that the basic function of an excitation system is to provide direct current to the synchronous machine field winding. This is a very simplest thing, that in any synchronous machine, right, we have to provide DC current or direct current, right, it operates. This is the main purpose of excitation system. Then the excitation system also performs various control and protective functions. We will see control and protective functions. These functions are essential for the satisfactory performance of the power system. That is, the modern excitation systems are provided with a variety of controls, right, and variety of protection functions. The very purpose of providing these control and protection functions are so that this excitation system can give you the satisfactory performance for the operation of the power system as a whole. As I told you that there are two functions, control functions and protection functions. Okay. Now, what are these control functions? Let us see. Control functions are basically, you can put at control of voltage and reactive power flow. In excitation system, right, we provide various controls so that we can maintain the terminal voltage constant under varying load conditions. I hope all of you are aware of the capability chart of a synchronous generator, where a synchronous generator operates in the given region in the PQ plane, okay. And this capability charge is decided from the consideration of overheating of the armature, overheating of the rotor circuits, or field system. Similarly, the small signal stability or stability considerations, right. Therefore, any synchronous generator is required to operate within the capability chart. In addition to this, the synchronous generator has certain short time capability also. So, that for a short time you can operate the synchronous generator to enhance the system stability, right, and they take advantage of short time capability of the synchronous generator. This short time capability is generally of the order of 30 to 60 seconds, right. And therefore, when I talk about the excitation system, it has large number of controls, right, and these controls are provided primarily to achieve these two goals. One is the control of voltage and reactive power flow. Okay. Second is enhancement of system stability. Okay. That is, the excitation system can be appropriately controlled, so that you can operate the system with larger tangent stability limits. Okay. That is called the enhancement of stability of the system. Then the protective functions. Why do we require the protective functions? Okay. The protective functions ensure that capability limits of synchronous machine, excitation system and other equipment are not exceeded. That is, you operate the system within the capability limit of the excitation, limit of the synchronous generator, limits of the excitation system, right, and any other associated equipment. As I have just now mentioned, that a synchronous generator has to operate within the capability limits, and that limits are obtained in the form of a capability chart. Okay. And this synchronous generator has a short time extra capability. It can supply extra reactive power, extra real power, but for a short time. Okay. And therefore, our controls are so provided so that we can use the, or we can take the advantage of this short time capability for improving the tangent stability, long term stability, dynamic stability of the system. Okay. But we provide in addition to these control functions, protective functions. So, that in case any of the capability limit is violated, right, the protection functions will operate, right, and keep this or operate in such a fashion, so that you operate within the capability limit. We should not go outside the capability limit, because any attempt of the system to go outside the capability limit means system is likely to be, or generator is life is going to be affected. Okay. Therefore, these are two important functions which you have to look into all the time: control functions and protective functions. Now, we can look into the excitation system requirements from two considerations. One is the generator considerations, from the consideration of synchronous generator. And another is from the consideration of power system, where synchronous generator is part of the large power system, right, and therefore, we will look into the excitation system requirements from the two considerations, one is generator considerations, another power system considerations. When you look into the generator considerations, the main function of the excitation system is to maintain terminal voltage as output varies. It has to automatically adjust the excitation current as the output varies and keeps the terminal voltage constant. This is one of the important requirement from the generator point of view. Second is that the excitation system must be able to respond to transient disturbances with field forcing. Now, this terminology is very important. There is, our excitation system should be such that whenever there is some transient disturbance, okay, and at that particular following that disturbance, if you want to resort to field forcing. Field forcing means we apply large voltage to the field winding of the synchronous generator, so that more current can flow through the field winding. That is, excitation current can be increased temporarily or for a short duration. Now, this field forcing capability is one of the important requirement of excitation system. As we will see that to have good field forcing capacity, the ceiling voltage of the excitation system, right, the ceiling voltage, when you design the excitation system, it will have a high ceiling voltage. Now, when you look from the power system considerations, then the excitation systems which are provided on synchronous generator should have effective control of voltage and enhancement of system stability. That is, we should be in the position to control the system voltage by controlling the excitation system, okay? And we should also be in the position to enhance the system stability. Okay. Second is, to achieve these goals, its response should be high, rapid response, so that you can improve the tangent stability. Okay. That we will talk subsequent in our subsequent, you can say, discussion, that how the rapid response or high response of the excitation system improves the stability of the system. Okay. But first we will understand what we mean by rapid response, how we quantify the dynamic performance of the system. Okay. Then we should have a provision to modulate the field current to enhance small signal stability. That is, when the system is oscillating, whenever there are some perturbations taking place, right, the oscillations are created in the system. The system is never in steady state condition, it is always in the quasi steady state condition, because load changes are taking place continuously. Okay. And whenever the load changes take place, generation changes, the load changes, and therefore, in this process of generation changing the load, right, the system is in the dynamic condition. Okay. And there are always small oscillations in the system. When I say small oscillations, magnitude of oscillation is small and the frequency is the low frequency oscillations, right. And there is a necessity to improve the damping of these oscillations by providing power system stabilizers, right. Therefore, the power system stabilizers are provided in the excitation system to enhance the small signal stability. Therefore, from power system consideration, I can say it should have the capability to enhance tangent stability. For improving or for achieving this goal, its response should be high, right, and then we should have the facility or capability to modulate the excitation system, so that we can improve the damping of the low frequency oscillations. Okay. Now, these are the requirements from the power system considerations. Now, let us see what are the main elements of an excitation system. The elements of an excitation system can be listed as exciter, regulator, terminal voltage transducer and load compensator, power system stabilizer, limiters and protective circuits. That is, broadly, if I look into the complete excitation system, then the various building blocks of the excitation system can be put as there is a exciter, there is a regulator, there is a terminal voltage transducer and load compensator, a power system stabilizer and limiters and protective circuits. Okay. Now, this is the block diagram which shows how these elements are interconnected or form the complete excitation system. Now, this is the main block where you can say this is our generator, a synchronous generator. This synchronous generator is connected to the power system. Okay. the field winding of the synchronous generator gets its current from exciter, that is the exciter supplies the field current, this is your exciter. Then the field, the output of the exciter is controlled by providing a regulator, this is the regulator. You can see here that regulator has number of inputs here. I will explain, okay. But one of the biggest or very important building block of the excitation system is a regulator, because here we are not talking about the exciters only, we are talking about excitation system. Okay. As I have told you that the primary function of the excitation system is to provide DC current to the field winding of synchronous generator, okay. And we provide various controls and protection system, so that we achieve the requirements of the system from the generator considerations and from power system considerations. Now, first let us look actually that we maintain the terminal voltage. How do we do it? We sense the terminal voltage from the synchronous generator terminals. Okay. Now, this is the block which shows the terminal voltage transducer and load compensator. I shall separately talk about load compensator, but you can understand that when I want to regulate the terminal voltage of synchronous generator, right, we sense the terminal voltage. Okay. Now, since the synchronous generator's terminal voltage is AC terminal AC voltage, it may be 11 kV, maybe 16 kV depending upon the design of the machine. Therefore, at this point the voltage is stepped down, okay, and then it is rectified and we get a DC signal which represents the terminal voltage of the synchronous generator. Okay. That is why what used is the terminal voltage transducer, that is you step down the voltage, you rectify and bring down to a level which can be used for the purpose of control. Okay. And this signal which is which represents the terminal voltage or a function of terminal voltage and load current, because we will be showing about the load compensator also. This is fed to the regulator. This is one of the input signals that goes to the regulator. Okay. The second block which I have shown here is the limiters and protective circuits. Okay. Now, the limiters will also sense the terminal voltage, load current, okay, and it is going to process these signals current and voltage which are sensed from the terminal of the machine, okay, and then we will decide whether the synchronous generator, the operating condition is within the limits or not. In case it is going outside the limit, it will take appropriate action. Again the action is taken through regulator. Therefore, this signal which is coming from the limiters and protective devices also is fed to the regulator. Then you have one feedback loop around the exciter. This loop is generally we call it the excitation system stabilizer. That is, here you sense the output of the exciter, okay, and in case you do not have this feedback loop, then the exciter itself may become unstable, because once you have a closed loop control system, right, the stability is a very important requirement, and therefore, you will find that there is one feedback loop, right, that loop is called excitation system stabilization, okay, and that again operates through regulator. And the last feedback loop is through power system stabilizer. You can see this power system stabilizer. Again this power system stabilizer takes its input signal from the generator terminal. The input signal to the power system stabilizer is generally the speed deviation. When a synchronous generator speed deviates from synchronous speed, this deviation is sensed. Another signals which have been tried are the deviation in the power output. Instead of sensing the speed deviation, you can sense the deviation in the power output, the delta P e, right, or deviation in frequency also has been looked into it, or a combination of these quantity, these signals. Okay. Now, this power system stabilizer is basically an auxiliary controller. It will operate only during the dynamic conditions, not during the steady state conditions, okay. And this also operates through the regulator. And any regulator, because basic function of the regulator is to perform all the required functions and maintain terminal voltage constant, and therefore, we have a reference. Therefore, input signals which come to the regulator, okay, they come through the terminal voltage transducer and load compensator, a voltage signal which is function of terminal voltage, and also the load current properly processed. We have to discuss in detail about this block. Then limiters, I have told you that we have to see that synchronous generator always operates within the operating limits, whether actually you want to use the short term capability, then still the limits are decided. Okay. We have to operate within the short term and long term operating limits of the synchronous generator. Then this power system stabilizer is to damp the low frequency oscillations, which are normally provided, or which happens because, or which exist, low frequency oscillations exist because of the perturbations which are taking place continuously in the system, and these oscillations need to be damped. They should not increase, they should not grow, otherwise system will become unstable. Okay. Now, these are the basic building block of a complete excitation system. Okay. Is it okay, or any doubt?
So, the terminal voltage transducer can function as a limiter also?
See, these functions are provided in a complex manner, but limiters have they just monitor magnitude of the voltage, okay, terminal voltage, magnitude of the current which is flowing through the synchronous generator, magnitude of the power which is output, real power, reactive power, not only one quantity, they monitor so many parameters. Because when I talk about the capability limit of the synchronous generator, then we look into the PQ plane. Okay. For a given value of P, there is certain value of Q possible. Okay. Therefore, PQ plane we have to maintain within that. Therefore, this is not only sensing the terminal voltage, but this limiter will sense all other parameters also. And not this block diagram is just to give you basic features of the excitation system, but it senses not only the generator parameters, but exciter parameters also. Exciter should also not go beyond its operating limits. Like, therefore, this is a separate, limiters means it just look, and the moment limits are crossed, it will take action. The action may be that it may even trip the synchronous generator from the system. Suppose it feels that now the synchronous generator is going outside the capability limit, then these limiters can even trip the synchronous generator. Okay. They are very I say actually that very complex control protective functions are provided, and our main consideration is that we take the best out of the synchronous generator, right, from the system point of view, and at the same time its safety is safeguarded, is ensured. Okay. Is it okay? Now, we will look into some basic performance measures. Here, as I stated that the excitation system control should be such that we are in a position to improve the stability of the system. Okay. and to improve the stability of the system, we have to look into what are the desired characteristics, okay, and therefore, we look into the dynamic performance measures. When the system is under dynamic conditions, what are the performance measures? Okay. Now, these performance measures are further classified into two categories, the large signal performance measures and small signal performance measures. That is, when the system is subjected to large disturbances, okay, we have to achieve certain performance measures related to large disturbances. Then whenever the system is subjected to small perturbations, okay, then we have to basically look into the stability of the system. Okay. Now, large signal performance measures, in the sense that suppose a 3-phase fault occurs in the system, or important transmission line trips, right, then the system is subjected to large perturbations, and at that time how the system should behave and how our excitation system and excitation control should behave, right. Therefore, we want to quantify what should be the dynamic performance measures of such a system. Now, related to the dynamic performance measures, there are some basic definitions we have to clearly understand. The excitation system ceiling voltage is the maximum direct voltage that the excitation system is able to supply from its terminals under specified conditions. It is the indicative of the field forcing capability of the excitation system. Higher ceiling voltages tend to improve tangent stability. This is a very important factor, that the excitation systems which have higher ceiling voltages, right, will have a higher field forcing capability and resulting tangent stability limit will be high. The next term is the excitation system ceiling current. The maximum direct current that the excitation system is able to supply from its terminals for specified time, right. Therefore, time is a constraint here. For a short time, it can supply current more than the rated value. For prolonged disturbances, this value depends on thermal duty of the excitation system. In typical excitation systems, the ceiling current is of the order of 1.6 times the rated current. The next important term is the excitation system voltage time response. The excitation system output voltage expressed as a function of time under specified conditions. That is, if I create certain control conditions, so that the excitation system for causes increase in the terminal voltage, and this increase is when it is plotted as a function of time, right, then that graph represents the voltage time response of the excitation system, right. Suppose I give an example actually, that suppose you make a step change in the reference voltage, right, the terminal voltage of the synchronous generator is going to increase, and if you plot voltage as a function of time, right, then that curve is the voltage response curve. Now, to quantify the voltage response, we define a voltage response time. The time in seconds for excitation system voltage to attain 95% of the difference between the ceiling voltage and the rated load field voltage under specified conditions. Now, just to illustrate this, suppose we this is the rated voltage, let us say it is 1.0. If I create terminal conditions or the voltage regulator operate in such a fashion, so that voltage is made to increase in this fashion, and let us say that this is the ceiling voltage, right. This is the ceiling voltage. Then we find out the difference between the ceiling voltage and the rated voltage, and the time which is required to attain 95% of this value. Let us say this time, that is, this is the 95% of the difference between the ceiling voltage and the rated voltage, and this time t, right, the time t in which actually the voltage will rise from rated value and it will attain 95% of the difference between ceiling voltage and the rated voltage. This is the voltage response time. Now, at the modern excitation systems have very high response, and we do specifically characterize the excitation system as a high excitation systems whose response time is 0.1 second or less than 0.1 second, right. That is, you have variety of excitation systems, okay, and those excitation systems whose response time is 0.1 second or less than 0.1 second are characterized as high response excitation systems. Then we also define a term which is called nominal response of the excitation system or excitation system nominal response. Now, to understand this excitation system nominal response, let us look at the voltage response of an excitation system. That is, here in this graph we are operating so that the excitation system output voltage is represented by OA, and the terminal conditions are so created so that the voltage increases and follows this graph or this curve, right. Then on this time axis we choose a time which is equal to 0.5 second, or this is represented by the line AD, okay. Then we draw a line, a straight line passing through this point A in such a fashion so that the area of this space, that is ABD, this area, the area ABD is equal to the area of this triangle, this ACD. That is, you are drawing, this is the actual response curve, okay. You draw a straight line such that this area ABD is equal to the area ACD, that is, the ACD is the area of the triangle. Then the slope of this graph represents the nominal response, and it is expressed as the slope here. The slope of the curve is, you can see the slope is CD divided by AD. You get this slope and you divide this slope by the rated voltage, okay, so that you get nominal response. Now, there is a reason for choosing this time 0.5 second for defining the nominal response. Whenever actually the system is subjected to the large disturbances, right, and the swing curve which we plot, the peak value of the swing curve normally occurs in the range, in the time range of around 0.4 second to 0.75 seconds. Of course, these figures are not very rigid, but when we subject a system to a large perturbation or large disturbance like a 3-phase fault, okay, then the swing curve when you examine, right, for a stable system the swing curve will attain its peak value in a time something like 0.4 to 0.75 second. And in case the excitation system is to come to rescue the system and improve the tangent stability, then it must act within this time. In case suppose it is slow and it acts after this time peak is out, right, then you cannot do anything, right. Therefore, the 0.5 second is the time which is being chosen and used. Now, we will talk about the very important performance measure, that is small signal performance measures. Till now what we discussed was the certain definitions which are related to the large disturbance performance measures or large signal performance measures. The small signal performance measures provide a means of evaluating the response of the closed loop excitation system control to incremental changes in the system conditions. That is, here these measures which we will discuss, right, these measures help us in understanding the behavior of the excitation system when small perturbations take place, right. Now, when we want to examine the performance of the excitation system when small perturbations take place, we use a linear model, that is, the system is linearized around the operating condition. Once we use a linear model, we can use the linear control theory to examine the behavior of the closed loop control system or the excitation control systems. Okay. The performance measures for small signal behavior or the small signal performance measures can be categorized or can be put in two ways. One is the making use of the time response, right, that is the indices associated with time response. Another is the indices associated with the frequency response, that is, we talk about the performance of the excitation system following small perturbations, either making use of the time response of the system or frequency response of the system. Okay. The indices associated with the time response are rise time, overshoot and settling time. Rise time, overshoot and settling time, these are the indices with which we can quantify the performance of or small signal performance of the excitation system. Now, to understand these terms, let us look at the step response of the excitation system. Now, this step response is plotted under no load condition for a closed loop control system, that is, when the generator is not loaded under no load condition, right, we obtain the step response. Now, this graph or this curve represents the step response of any closed loop system, right. Just see this is step response. Okay. Now, if we have given a step input equal to 1 per unit, that is unit step input, then this is the steady state value, that is under steady state condition, right, the output of the system should attain a value equal to 1, because we have given step input or unit step input. Okay. Now, The method of defining this rise time is that you look at this 10% value, that is 0.1 per unit value, look at this on the graph a time corresponding to the 0.9 per unit value, okay, and then the time required for the response to rise from 0.1 corresponding to 0.1 to 0.9, right. This time is called the rise time. The lower the value of this rise time, the response is fast, okay. The another measure is the overshoot. You can just see here, this is the overshoot actually, this is the steady state value, this is the positive peak, and therefore overshoot is defined by this value, okay. Therefore, this is another measure for characterizing the dynamic response or small signal response. And third is the settling time, that is the time in which the response settle to the steady state value within certain specified limits, because you will find that this response is going to have some oscillations, okay, and the moment it comes within these limits, right, then this time is called the settling time. That we have not to wait till it attains the value equal to 1, the moment it comes in this band, which is the permissible band, right, that is the specified band for settling time, right. Now, this band is again different actually, but normally we can have 5% plus minus 5% band. Therefore, once it reaches within plus minus 5%, okay, then this is the, therefore, these are the three important parameters which characterize the small signal performance of the excitation system. The another indices which are used making use of the frequency response of the excitation system. The indices associated with the frequency response are low frequency gain, crossover frequency, and phase and gain margin. They are the three important parameters. Before I talk about these three parameters, I would like to highlight here that since it is a closed loop control system, therefore, stability and the degree of stability, these are of paramount importance, okay. And another thing which we need is that the closed loop control system, we want the low steady state error. Steady state error should also be low, because suppose I want to regulate the terminal voltage, right, then I want to regulate the terminal voltage within a small band, and that the steady state error will depend upon again the characteristic of the excitation system. And as we will also see actually that these requirements are conflicting. Suppose you want to achieve very low steady state error, then the stability may have to be compromised, right. Therefore, there are conflicting requirements. And in the frequency response, these are the three important indices: the low frequency gain, crossover frequency gain, and phase and gain margin. Now, here here I think to illustrate this, let me see. See, the any control system can be put in this form. Okay. that is the G1 and G2 are the transfer functions, right. And now what happens is that when we are interested actually in plotting the frequency response of this system, we plot the frequency response of these two transfer functions G1 into G2, right, G1 into G2, or you can call it actually the open loop transfer function, open loop transfer function. Now, this graph shows the frequency response of open loop transfer function of a typical system. Okay. Now, when you plot this graph, we plot two curves. One is the gain, another is the phase angle. We plot phase angle and gain. The gain is plotted in decibel, that is gain in dB. Now, the gain in dB is defined, that is gain in dB is equal to 20 times the log of G1 G2. That is, this G1 G2 is the transfer function of the open loop system, okay. And G1 and G2 both are function of Laplace transform S, right. And when we plot the frequency response characteristic of the system, then on x axis we mark frequency, and on y axis we mark the gain in dB. Okay. This is the very standard terminology used, and since G1 and G2 both are function of frequency, right, therefore magnitude and phase angle of this open loop transfer function vary as the frequency changes. Now, this graph you can just see that this is a typical graph, this is a typical graph, I hope it is visible. A typical graph is shown like this. That is, this is the gain, this is plotted in dB, okay, and this is the frequency, and then you will see actually that these are plotted actually in the logarithmic scales. The frequency is also marked in log of omega n. Okay. Now, the low frequency gain is shown here. Actually, when the frequency is low, this is the gain, right. The higher the value of this low frequency gain, right, the steady state error is going to be low, right, because when the system is under steady state condition, right, then at that time the system is not the omega becomes 0, you can say, right. Therefore, at very low frequencies, or actually when omega is 0 steady state condition, this gain will represent the steady state error. Higher this value, lower will be the steady state error. Then this is there is a frequency here at which this gain becomes 0. This is called crossover frequency. This is the crossover frequency. Now, similar to this graph, on the same diagram we plot the phase angle characteristic. Now, typical phase angle characteristic is shown here like this. Now, on this axis we are marked the phase angle in degrees. Okay. The frequency at which the gain becomes 0 is called crossover frequency, and higher is the crossover frequency, better will be the response. Okay. Now, when we talk about the gain margin and phase margin, now to understand what is the meaning of this gain margin, you look at the phase characteristic or phase angle characteristic. Now, you can see here actually that when this phase angle for this particular frequency, the phase angle has become minus 180 degrees. Okay. Now, corresponding to this phase angle, at this frequency, I find out what is the gain. For example, for this phase angle is minus 180 degrees, the corresponding gain is this, and this gain is called gain margin. Gain margin, this quantity is called gain margin. Now, then we also specify what is the phase margin. To specify the phase margin, what we do is that we look at the crossover frequency, what is the phase angle of the system at the crossover frequency, what is the phase angle of the system, and let us say phi c is the phase angle at the crossover frequency, and this difference, this 180 minus phi c, this represents the phase margin, this quantity, that is the phase angle corresponding to crossover frequency and the phase angle and this 180 degrees phase angle, right. This difference is called phase margin. Now, for any control system, higher the value of gain margin and higher the value of phase margin, higher is the stability of the system. Okay. Now, we can see one very interesting thing here, that suppose we want to increase the low frequency gain. Now, for increasing low frequency gain means I increase the gain setting of this block G1 or G2. Okay. Now, when you increase this gain setting, means this graph will go as a whole up. That this graph, to make this quantity more, this graph has to be shifted up. Now, when you are doing this, shifting this graph up, both this term, this GM will reduce, that is the gain margin will reduce, and phase margin will also reduce. And this very clearly shows actually that when you are trying to tune one parameter, right, the other, it has a detrimental effect on other parameters, other aspects. Okay. And in field actually the AVR tuning is a very important exercise to be performed, where the gain setting and other parameters are to be set, so that we obtain a certain amount of phase margin, gain margin, and actually the desired steady state error. One more important parameter, there are not one but there are two more parameters which are also important, which are obtained from the frequency response characteristic. And here we plot the frequency response of the closed loop system, that is G1, G2, right. This loop is closed, that is the feedback loop is closed, and the generator is disconnected from the system, that is generator is not loaded, under unloaded condition. Okay. Now, the graph which is plotted here is, one is this graph, that is the gain, you just see this graph for gain like this, and then there is the phase angle. Okay. Now, the peak value of this graph, that is generated by MP, let us say MP is the peak value which occurs at a frequency omega m. Now, this peak value also represents the overshoot in the time response. It has a relationship between it is a relationship with respect to the time response. If this peak value is high, then the overshoot is also going to be high. The another term which is used is the bandwidth. Now, to understand this bandwidth, if we plot a graph, that is omega versus the gain, in dB, right. Let us say for a typical, I am not showing this overshoot anyway, let us like this. Then in case suppose I instead of plotting gain in dB, let us say the actual gain, let us say this is 1.0 and the frequency at which is drops to 0.707, right. Then this frequency is called bandwidth, and if I plot the graph in terms of gain in dB, then this point will become 0, because right, if I take the log of 1 to the base 10, it becomes 0, right, and this will become -3. That is, on this, in the same graph you have plot gain in dB, then this is 0, this is -3, and therefore this, the bandwidth is determined by plotting the frequency response of the closed loop system. Okay. For any particular system to have good characteristic, the features are the gain margin should be 6 dB, phase margin should be about greater than 40 degrees, greater than equal to 40 degrees, and overshoot should not be more than 5 to 15%. That is, overshoot is around 5 to 15%. Now, let me conclude here that we have discussed the excitation system requirements, performance characteristics, the performance characteristics related to large disturbances and small disturbances. For small disturbances, we have discussed the time response as well as the frequency response. Thank you.